And last time we talked about some of the particles that we typically see in nuclear reactions. We have alpha particles, which can be abbreviated with a 4 or a 2, and the alpha symbol are helium. We also have beta particles, which is 0 minus 1 with the beta symbol, are also an E for an electron. We also have gamma, which is basically just the gamma symbol, 0 and 0. Then also we have some other things like protons. So a P or a hydrogen there as well. We also have neutrons, and we also have positrons, which again uses kind of the same symbols as a beta particle, except that it is +1. So these are the common sort of symbols that we come across in nuclear chemistry. Remember, in nuclear chemistry, it really is all about sort of what happens in the nucleus. So we change protons, neutrons, and because of that, we do end up with really no conservation of elements. And that's very different than a chemical reaction where basically make bonds, break bonds, I guess break bonds and then make bonds perhaps. And that all involves electrons. We never touch anything in the nucleus in a chemical reaction. So that's why we always have sort of the conservation of elements. That's why when we balance the equation, we have the same elements basically on both sides, the same amount. But here in nuclear chemistry and nuclear reactions, it's very different. It's all about basically changing what's in the nucleus. So that also changes, as we talked about at the very end, sort of how we balance equations and how we balance nuclear equations. So when we do balance a nuclear equation, basically there's just two things that you have to make sure of is when you add up all the mass numbers on the left hand side, they need to equal all the mass numbers added up on the right hand side. And secondly, all the atomic numbers on the left hand side need to equal all the atomic numbers on the right hand side. So uh, not incredibly difficult to balance nuclear equations. Really, a periodic table is your friend. We talked about a couple of sort of words and stuff that are sometimes used in these sort of equations. If you have, again, anything that decays through, say, alpha decay, beta decay, or whatever it may be, or that it emits some type of particle, those sort of words mean that the particle will basically be on the product side. Now, we also have some reactions, the nuclear reactions, where we bombard something with, say, like a neutron, or there's like an electron capture. If it's any of those type of words, then those particles will end up on the reactant side. And as we talked about, there's really kind of two versions of balancing nuclear reactions that you come across. One is you basically have the reaction and something's missing. And that's a very common sort of way. And secondly, you're just told like this thing goes through an alpha decay, and that's sort of all you're given, and then you kind of write your equation from that. Remember that the atomic number is the number of protons, which is found on the periodic table, and every element has its own unique, obviously, atomic number and number of protons. So that's usually a really good place to start with if you're trying to figure out what it makes or what we're looking for that's missing. Once you do that, you can then figure out, obviously, the mass number associated with it. Any questions on any of that there? All right, so why don't we try one here? PO 212 decays through alpha emission. Write the balanced nuclear equation for. Okay, so let's take a look at this. So here we're going to start with our 212 PO, and it is going to decay through alpha emission. So again, emission means that that particle will end up on the product side, and you can use the alpha symbol if you want. You could also, if you wanted to, use the helium symbol. They're both okay, whichever way you kind of want to roll with it. Now, obviously, we could go to the periodic table here and find our missing atomic number for PO, which is 84. And now we really want to figure out what is it going to sort of form here. So once again, we could start with the atomic number. We got 84 on this side. We have 2 on this side. So if we subtract that, that gives us 82. That is the missing atomic number that we need to balance out the atomic numbers on each side. we once again would go to the periodic table and find number 82 there. Looks like lead is a winner. And now for our mass number, we're going to do the same thing. We got 212 here, and we got 4 there. So again, if we take 212 minus 4, it's like 208 maybe. Yeah. And that's going to give us a 208 here. And this would be, again, our balanced nuclear equation. We add up the top numbers. We got 212 working on both sides and 84 on both sides as well. Any questions on that there? So as we touched upon a little bit here, and again, just to sort of reiterate, chemical reactions really just involve electrons, and again, either gaining or losing. We really don't do anything with the nuclei or the nucleus, basically. Nuclear reactions, as we've been talking about, is very, very different in that sense that it's all really about that. We convert protons to neutrons, neutrons to protons, and because of that, we again will typically form new elements as a result of these reactions. Also, because we're playing kind of within the nucleus, it takes a lot of energy to kind of convert certain of these things out, which is why they do release a certain amount of energy as they kind of form the new nucleus that's being formed. So take a look a little closer at the beta decay here and some of the decay processes that we undergo. And we're not going to worry about this. It's just a neutrino, so we're not going to do anything about it. It pretty much has 0 and 0. But what's happening here is we can see our beta particle being emitted, and we're going from carbon 14 to nitrogen 14. Again, here we end up with the same mass number, but our atomic number does change by 1. Since it does give off a -1 for the beta particle, we actually go forward on the periodic table by 1 to balance it out. So what happens in this particular case is we're actually converting a neutron into a proton in this process, and the neutron is getting converted into a proton. It's releasing a beta particle as a result of that. Now, you may say, well, obviously neutrons and protons are changing, but we do end up with the same mass number. And if you sort of go through it kind of step by step here, it is going to lose a neutron, which means it will then drop to 13 and 6. It will then convert that neutron into a proton, which means it will gain a proton in both locations, up here and here, and it will now go to 14 and 7 and then to nitrogen and then make our beta particles. So although it appears that the mass number really doesn't change, it actually does change. One of the neutrons go away, but then we basically put back in a proton. So overall number for our mass number basically remains the same, but there is that conversion of a neutron into a proton when we have a beta decay. When we look at a positron decay, same idea. We're going to convert actually a proton into a neutron. So they're the opposite of a beta decay. And once again here, we see our atomic number go down by 1 as we give off a positron. And once again, our mass number does appear to stay the same, but it's kind of the same idea. We take the first one here. We're going to lose a proton, which means that we will lose a number on top and a number on the bottom, which again will take us to 5, which now take us to boron. It then will produce a neutron, which will then put a number back up there, since that's protons and neutrons. And again, that is how we get back to really our mass number ultimately being the same number. But here again, we did swap basically a proton for a neutron, and there is some change that is occurring in this process. Any questions on that there? Now, an electron capture is pretty much what it sounds like. Somebody's going to grab onto an electron, and here we are having the electron here on the reactant side, and that's very common for an electron capture. In this case, not too bad. We just add those two numbers together, and we get 17, which is what our new atomic number would be on the other side. What's again happening in this case is a proton and electron are coming together and actually going to make a neutron in this case. And it is kind of the same idea as what we saw earlier. We're going to basically lose a proton, which will take us from 37 to 36 and from 18 to 17, which is how we get to chlorine. But we are going to make a neutron, which will then put one back there. And now we're back to 37 up there on top. So once again, although it appears that the top number really doesn't change, there is some changing that's going on here. And in this case, we're kind of giving up a proton and making a neutron in this case. Probably the biggest change that you have is the alpha particle. You get a change of 4 for the mass number and a change of 2 for the atomic number. And we do get the biggest sort of decrease. Now on the bottom there is a spontaneous fission reaction. And let me write it a little higher so you could actually see it there and not get cut off by that. 49 IN plus 2 neutrons. Now this is a fission reaction, and once again it's a spontaneous fission reaction. And this is basically what happens in a fission reaction is something will be unstable and it will split off into 2 new nucleuses. In this case, actually it's 2 of the same, but very often it's different nucleuses that happen. And in fact, sometimes you can't really predict what you're going to get when this process occurs in terms of the products. And what usually happens in a fission reaction is in addition to making 2 new nucleuses, we also will definitely release some neutrons in this process, and usually a good amount of energy is going to be released in this process. So this could happen sort of spontaneously. This also can happen by what's sometimes referred to as transmutation, where basically you shoot a particle at something, makes it very unhappy, and then it will go through that process when it becomes unstable and go through a fission process. That is, by the way, the fission reaction, as we'll talk about, is the reaction that is used, for example, in like nuclear power plants and stuff like that. But they sort of force that reaction to occur by shooting neutrons at uranium, and they kind of start this fission reaction. Again, it gives off a lot of energy in that process. Here's a table from your book. You have a similar one, again, that describes all of our sort of changes that are occurring there. All right, so I want to take a moment here. Let's write the balanced one for potassium 40. When it goes through a positron emission. All right, so when we do see an isotope written like this, potassium 40, this number here is the mass number. And again, I know that because I can find the atomic number right there on the periodic table, and it's clearly not 40. So that is where we're going to start with here. So we'll start with potassium 40. Once again, we could go to our periodic table there and find our missing atomic number, which is 19 in this case. This is a positron emission. So emission means that the positron particle will be on the product side. And your option as to how you want to kind of do that. You can use, again, kind of the beta symbol. You also could use the electron sort of symbol with a +1, whichever one you prefer. At that point, we now got everything we need to kind of find what is missing there. I got 19 on the bottom and +1. That means that my missing atomic number is going to be 18, which will give me 19 on both sides. Go into periodic table, 18 there is argon. For my mass number, I got 40 on the left, 0 on the right. So to balance that out, we will need a 40 in this case. Any questions on that there? Not too bad, hopefully. All right. All right, so take a moment here and balance each of these and see what you come up with. Okay, so let's take a look, see how you're doing. So once again here, uranium-238, the 238 being the mass number. Here we have an alpha emission. So that tells us the alpha particle there is going to be on the product side. Again, you can use helium or the alpha symbol to do so. We're going to throw our uranium-238 on our reactant side. We could go to periodic table there and find the atomic number for uranium, which is 92 in this case. That is going to give us our missing atomic number, which would be 92 minus 2, which is 90. Once again, we go back to the periodic table and find number 90, which is TH. Now for our mass number, we got 238 on the left and 4 on the right. So 238 minus 4 is 234 in this case. Yeah. Questions on that one there. All right, neon 24, we got a beta emission. Once again, emission means our beta particle there is going to be on the product side, and we will have our neon on our reactant side. And again, we could go to the table there and find neon's atomic number, which is 10. In this case, if we get our missing atomic number, it is 10 plus -1. So we do need our subtracting 10 minus -1, which means we'll actually end up at 11. We do have to go one more above. 11 and -1 gives us 10 on the bottom. Going to our periodic table there, number 11 being sodium. Mass number 24 on the left, 0 on the right gives us a 24 in this case. Any questions on that one there? Positron emission, again, means our positron particle will be on the product side. You can use the beta or the E for the symbol for that. Nitrogen 13 going up on top. Periodic table, nitrogen number 7 there. And in this case, 7 minus 1 is 6. So we will end up with 6 as our missing atomic number. And obviously number 6 there is carbon. And up on top, 13 on the left, 0 on the right. So 13 are missing mass number in this case. Lastly, we have an electron capture, and we're going to start with our beryllium 7. We again go to the periodic table, get the atomic number, which is 4. Electron capture means that that electron is actually on the reactant side. So that's one of the few times that you will hit something that's going to be on this side. And we use our E with our -1. In this case, all we have to do really is just add the bottom. So we got 4 plus -1 is 3. Again, go in the periodic table, number 3 is lithium. Up on top, 7 minus 0 is 7 in this case. Any questions on balancing nuclear equations? We just do a whole test of these. No, I'm just kidding. Any questions on that there? Or not? All right. All right, the next thing we're going to actually talk about is something to do with stability. And there's a few ways that we look at stability. And one of the ways we look at stability is through what is sometimes referred to as the N to Z ratio, or the neutron to proton ratio, right? So N is neutron, Z is the atomic number, which is the protons. And depending on this ratio, it will help you decide whether or not a nucleus is going to be stable, or a nuclei. And there is, as we will see on the pictures very shortly, there is what is sometimes referred to as this belt of stability or valley of stability, which is a nice, good ratio for things to be stable. Now, what happens though, a lot of times, especially with things that are radioactive and not very stable, is they fall on one side of this valley or belt, whatever you like to call it, or the other. They're either kind of too high or they're too low. And the idea is if their ratio is too high, what will happen is neutrons will be converted into protons, and it will go through a beta decay if it is too high. And what it will essentially do by doing that is it will bring that ratio heading towards the kind of stable ratio. Will it perfectly get it back to being stable? The answer is probably not, but it will move it towards it. In some cases, it may actually get it to a really stable ratio, but it definitely should move it towards becoming a little bit more stable. Now, if you end up with a ratio that is too low, you're kind of on this side of the valley of stability. What will happen is the protons will be converted to neutrons, and that will basically kind of bring the ratio back up. And there's actually two ways that you could do that. You could either do a positron emission or an electron capture. And you could also do an alpha decay, but it's not as efficient. So for us, we will stick to these two. but technically you could still do an alpha decay. Now you might be asking yourself, why do I have an option maybe of two different ways? One, I maybe get a different thing. We could actually use an example we just looked at here, which was beryllium-7 there. And what we did on the beryllium-7 was we did an electron capture, and what we ended up with was 3, 7, and lithium. So that was an electron capture. If we started with the same beryllium, but instead of an electron capture, we did a positron emission, we would end up with something that looks like this. And again, if we did our math, we would actually end up with the exact same product. So they both will end up with the exact same product if you do a positron emission or you do an electron capture. So you do have the option. And again, the idea here is to kind of bring everybody to a more stable sort of ratio. And like I said, in a lot of cases, it may not be perfectly stable, but it should be getting better. And in some cases, you may actually get it to be better. So as I mentioned before, there is sort of a ratio that is really good. And this sort of yellow smear here is the belt of stability or the valley of stability. And again, we're either going to be too high or too low. And how do we know what is a good ratio or not? It has to do with the atomic number of what you're looking at. So if your atomic number is anywhere between 1 and 20, an acceptable good ratio there is a ratio of 1. And again, if you're between 20 and 40, an acceptable ratio is 1.25. If you're between 40 and 80, it is 1.5. And if you're above 83, which means 84 and above, there is no good ratio. You're basically going to be radioactive for sure. Now, for us, we're going to use these as hard cutoffs. So either it is 1 or it's too high or too low, or either it is 1.25 or it's too high or too low, or it's 1.5, it's too high or too low. I say that because books and people, there is sort of a grayish area. If you look here, this ends at 20, but this begins at 20. So there is sort of an acceptable kind of grayish area in between there. If you kind of fall in the 20-ish range or something like that, well, it's a little bit high, but it's still lower than the next guy. So it's still sort of okay. So for us, we're just going to do sort of a hard cutoff. So we don't have to worry about any sort of gray area, but you may come across some in the book or homework or something like that that does sort of fall in that grayish area. So it does happen. Let's see here. So let's take a look at one here. So why don't you give it a try? Magnesium 22. We want to know, is it stable? And if it is not, what type of radioactive decay will it go under, and write the equation for what it will go under. And magnesium on the magnesium 22 is the mass number. We can go to the periodic table here and find the atomic number, which is 12. We are looking for the N to Z ratio here, so we want the neutrons and the protons in this case. Obviously, our protons there are going to be 12, which is our atomic number. Our neutrons is going to be our mass number, which is 22 minus 12, and that is going to get us 10, I believe. So to calculate our N to Z ratio, we'll take our 10 neutrons, we'll divide it by our 12 protons in this case, and that's going to get us like a 0.83, I think, 0.833. Now, since this is an atomic number of 12, that falls between the 1 to 20 range, where an acceptable stable ratio is 1. And in this case, 0.83 is less than 1, which means we are a little low. So we're kind of on this end. So we need to bring it up. So in this case, when we are too low, you have one of two options. Your magnesium will then undergo some decay process, which can be an electron capture. And when it does so, 12 and minus 1 is 11. 11 on the periodic table is sodium. And up on top, 22 minus 0 is 22. Or it can do a positron emission, where 12 minus 1 is 11. and that again is sodium, and obviously on top is 22, so it can do either one of those. First off, any questions on that there? If we now look at what we just formed through this radioactive decay here, we now have a mass number of 22 minus an atomic number of 11. That is an 11 for our neutrons. Our number of protons in this case is 11 because that's the atomic number. So for our new guy, if we calculate our ratio, that's 11 divided by 11, which is 1, which actually in this particular case did actually give us a pretty stable ratio. It will not always be that way. Like I said, it should definitely be moving towards the stable ratio. You may not always hit a perfect ratio, after 1. You do not need to keep going until you get something that's perfectly stable. You just need to do one of the decay processes there to show that it's moving in that direction. Any questions on that there? All right, let's try another one here. Let's do Krypton 85. Is it radioactive? And if so, what type of radioactive decay will it undergo? What will it produce? Krypton is 36 there on the periodic table. Okay, so let's take a look. So Krypton 85. 85 is our mass number. Once again, to the periodic table there for 36, which will give us our atomic number. We're looking for our neutrons and protons. So obviously our protons is going to be 36. Our neutrons is going to take the mass number, top number, minus the atomic number. And that's going to get us here 49er there. Now calculating our N to Z ratio, we'll do 49 divided by 36 in this case. And we will end up with a ratio, we'll call it 1.36. Now Krypton will fall in the 20 to 40 sort of category of ratio. And that acceptable ratio is 1.25 in this case. And obviously here, 1.36 is higher than 1.25. That means it's unstable and it will follow a beta decay to bring it back down. So if we did that, we would have 8536 in Krypton. It will do a beta decay. Remember that is -1, which means we actually need to go 1 up so that we end up with 36 there. So to 37. 37 is RB. Up on top, 85 minus 0 is 85. So this is what we would expect to happen. Now, again, if we kind of check what we just ended up with, we have protons, that's 37, neutrons, that's 85 minus 37, and that's going to get us here about 48. So the new kind of N to Z ratio is 48 divided by 37, and that is about 1.30. It didn't get tremendously perfectly stable, but it did move in the right direction. We're at 1.36, and now we've dropped it down to 1.3, heading towards the 1.25, which is considered stable. Any questions on N to Z ratio here? So that is one sort of thing that we look at in terms of stability. Now, there are other things that sometimes we do look at in terms of stability to help us maybe make a decision. And the first thing that we could look at is the number of protons and neutrons that something has, and whether or not it is sort of even or odd for those things. Really, the best situation that you could have is if you have an even number of protons and an even number of neutrons. There's like 100 or whatever it says there, 157 stable nuclei with that situation. So best situation is even of both protons and neutrons, probably a fairly good shot. You're going to have something that's going to be stable. The next sort of best thing is even protons, odd neutrons. There's about 55 that are 53 that are stable. Next best thing is odd protons, even neutrons. There's about 50 that are stable. The worst case scenario is when you got odd and odd. There's only about 5 that are stable nucleides. And again, that's the worst situation. So best situation, even. word situation odd and odd. And again, that's another common way that we sometimes look at stability. The total number of nucleons, and you sometimes will see this word a lot in nuclear chemistry. Nucleons is a fancy way of saying the particles within the nucleus. So that usually is your protons and neutrons. So those are the guys that are hanging out in the nucleus, also known as your mass number, pretty much. They are stable when it adds up to a magic number. The nucleus is more stable, kind of like noble gases. This is a really stable electron configuration. It is most stable when you have neutrons or protons that equal 2, 8, 20, 28, 50, 82. And your mega number there is 126 there for neutrons. So that's, again, just some stable sort of numbers that you sometimes can come out. Probably, again, neutron to proton ratio is probably a really good thing to look at. And again, even, odd, that's also a pretty good thing to look at. Let's talk a little bit about a decay series. And in a decay series, it is a long process where a radioactive nuclei basically just continues to go through these decay processes. And they will continue to follow this decay series until they sort of hit a stable situation. What we start with, again, is sometimes referred to as the parent nuclei, and what we make is the daughter nuclei. And if you are doing a decay series and you need to know kind of what everything is along the way, you can basically just do it like we did with our balancing equations. You can just write a balanced equation after a balanced equation after a balanced equation, and you can figure out what you kind of make along the way in this process. You also can shortcut it if you're involved alpha or beta decays. If you're maybe just interested in kind of what you get at the end rather than maybe every step along the way. For every beta decay and for every alpha decay that your process goes through, for alpha, we will subtract 4 from the mass number and 2 from the atomic number. And for every beta decay, we will actually add 1 back to the atomic number. So you could kind of shortcut it in a sense. So for example, if we took uranium 238 and 92 is its atomic number, it'll just say, it went through a kind of short decay process. Do something like, let's see the first few of those: alpha, beta, beta, alpha, alpha, beta, beta, and alpha. So if you wanted to sort of do it like we did our nuclear equations, what you would do is you would start with your uranium-238 here. And the first thing that's going to happen is it's going to go through an alpha decay, which means you can just write an equation like you were doing nuclear balancing equations. And we would find our missing number like we did previously. That's a 92, that's a 2. And our missing atomic number would be 90. We again would go to the periodic table, and number 90 is TH. We would then do our top, which is 238 and 4, which will leave us a 234. What happens though now is whatever we just formed is what's going to start the next reaction. So we'll take what we just formed, and now that thing will go through the next process, which is a beta decay. So again, we could just write our reaction like we were doing a normal balancing equation. We have our beta decay. Here again, we do need to go up 1 to 91 so it balances. 91 and -1 gives you 90. We go back to the periodic table. Number 91 is Pa. And 234 minus 0 is 234. So that is our second sort of product in this decay series. Then we would take our second product that we made, and that guy would go through the next decay process, which again is a beta decay in this case. And again, 0 minus 1. So again, we need to go 1 up to 92. 92 and -1 is 91. 92 on the periodic table takes us back to uranium, and we're at uranium-234 at this point. And lastly, in this kind of abbreviated decay process here, we would take our 234 92 uranium, and that would go through our last little decay process here, which is an alpha decay. And that is 4, 2, and alpha. Missing atomic number going to be 90. Missing mass number there going to be 230. 90 again on the periodic table is TH. And that again is the way you could kind of figure out a decay process, sort of what you get after every shot there. Just basically write an equation. Whatever you make on the first equation will then become like your reactants on the next one, and you keep doing that. This is obviously not the end of this decay series. It will continue down until it hits something that's stable. In this case, it will continue all the way down until it hits lead, basically, and follow through. Now, earlier we were talking about that, if you're maybe just interested in what you get at the end of this process, you could just start with the numbers here. And basically we have 2 alpha particles, which means from the mass number, we're going to subtract 4 twice. And from the atomic number, we're going to subtract 2 twice. And we got 2 beta particles, which means we're going to add 1 to the atomic number. And we're going to do it twice since we have 2 of them. And now you can just add up what you ended up with. So obviously there, 238 minus 4 is 234, minus 4 is 230. 92 minus 2 is 90, minus 2 more is 88, plus 1 is 89, plus 1 more is 90. And you end up, obviously, with what we got going on right there. So if you're doing a decay process that involves just alpha particles and beta particles, you're not really interested maybe in every little thing in between. You could kind of just do that quick math and figure out what you get at the end. Any questions on that there? So as I mentioned, this decay process, here's the one we just sort of did a little bit of for uranium-238. It actually splits off, as you can see. It will continue down this path, and then it will sometimes go that way, sometimes go that way. But eventually, it will continue down all the way down to lead-206, which is a stable nucleus. So again, this process just continues to repeat until it hits something that's relatively stable, and it will sort of stop at that point. Any questions on a decay series here? So the next thing we're going to actually talk about is the kinetics of radioactive decay, and this is kinetics. The good news or bad news, I guess, depending, I suppose, is it is the exact same kinetics that perhaps you learned in the last class. All radioactive decay follows first order kinetics. So they all follow first order kinetics. And basically, first order kinetics is the same formulas that you might remember. A little natural log of A is equal to the natural log of A naught minus KT, where the half-life is equal to the natural log of 2 divided by K in this case. Now, this is basically the integrated rate law for first order kinetics. This is the half-life equation for first order kinetics. And this goes with a graph that is very typical that you see for first order, and that is the natural log of A is equal to minus KT plus the natural log of A naught. That is in the form of y equals mx plus b, a straight line. And if you graph that, take the natural log of A versus time, you would yield yourself a straight line where the slope of that line equals negative of the rate constant. In this case, with nuclear chemistry, we sometimes don't use the same symbols. So sometimes nuclear chemistry likes to use some of their own symbols. So you will sometimes see instead of A, which by the way here is typically your final concentration, this is your initial concentration. This is, in traditional kinetics, the rate constant. In nuclear chemistry, it's what's known as the decay constant. And the T here, by the way, is time. It is not temperature, so it is time in this case. Now, in nuclear chemistry, sometimes they will use the natural log of N to stand for nuclei, equals natural log of N naught minus KT. And again, this is your final nuclei. That's your initial. This is your decay constant, which is like your rate constant. And again, that is time as well. Now, unlike in traditional kinetics, if you remember, in traditional kinetics, we oftentimes will use concentration or molarity. In nuclear chemistry, you could use anything you want. So you could use concentrations, which is very rare. You could use like grams for both things, the A's. You could use, milligrams for both. You could use actually a rate of radioactive decay, like so many counts per minute. So you could actually, for the N's or the A's, you could actually use any unit you want to put in there as long as they are both the same unit. So everything cancels out correctly. Now, very often, as I mentioned, you also sometimes see instead of K, they'll use lambda for the decay constant. Sometimes nuclear chemists like their own little symbols and stuff like that. But I think most books nowadays will just still roll out with the kind of traditional kinetics sort of one here. And you can as well. Now, the other thing that's important is very common in these type of problems. You need to use both of these equations sometimes together. So very commonly, they will give you the half-life, and they will give you a bunch of information up here, but you're missing the decay constant. So it's a very common sort of move that you have to do, which is use the half-life equation to figure out the decay constant and then use the other formula. So very commonly, you kind of have to use them together. Just a reminder that when you look at the decay constant for first order kinetics, usually the units are 1 over some unit of time, like 1 over seconds, 1 over minutes, etc. Now, a very common error that people make when they use this integrated formula, the back end of it here, is they have these guys in different units of time. So you do want to make sure that the time and the decay constant are both in the same units of time. Otherwise, you're going to be off. So if you have one in minutes and one in years, that's not going to work out well for you. You do have to do some type of conversion for them. Now, here's some half-life of some things, and you can see half-lives do depend on what you're dealing with. Some can be super long, like uranium-238. Half-life is 4.5 times 10 to the 9 years. Unfortunately, I don't think any of us make it to a half-life of that. Some can be really, really quick, like you see TH219, 1.05 times 10 to the minus 6 seconds. So just like that. Usually about 10 half-lives, it's gone, right? It's not too bad for you at that point. As we'll talk about a little later on in this chapter, obviously, if you're using something for medicine or something like that, you usually want a very short half-life, right? Otherwise, again, the follow-up appointment is way, way down the road and stuff like that. But again, things can stick around for a long time. And that's, as we'll talk about as well in this chapter, one of the issues with like using a uranium for those fission reactions in a nuclear power plant. It hangs around a really, really, really long time. And the products that it makes hang around a really, really long time as well. So let's take a look at one here together to see how we approach this. If you have 1.3 milligrams of plutonium-236, we want to calculate the mass that will remain after 5 years. And one of the things they give us is the half-life here is 2.86 years. So the good news is, since all radioactive decay follows first order kinetics, the equations or formulas that you use is always the same. It is basically this equation. We'll just use the regular kinetics equation and the half-life equation. So these are basically always your choice of kinetics formulas for radioactive decay. These are, again, both first order kinetics that happens here. So in this particular case, we have 1.35 milligrams. So that is our initial concentration, 1.35 milligrams. We're looking for how much will be there at the end. And at the end, that is a total of 5 years here. So if we look at our integrated rate law, which deals with concentration and time, we are looking for this guy. We have this guy. We have our time. As I mentioned a second ago, in this particular case, we are missing the decay constant. And that is where the half-life comes into play. So we could use the half-life and the half-life equation here to actually solve for the decay constant so that we could actually use it to solve for what we're looking for. If I rearrange the half-life equation, the decay constant will equal the natural log of 2 divided by the half-life. Natural log of 2, by the way, on your calculator is 0.693 if you do that, divided by our half-life, which is 2.86 years. That's going to get us a decay constant in this case of 0.693 divided by 2.86. Going to get us a 0.2424. The units here are 1/years. And again, that is the common units for a first order reaction. For the decay constant or the rate constant, it is 1/unit of time. Now, this is everything that we need. We can now put it in there, the natural log of our final sort of concentration, going to equal our natural log of 1.35 minus my decay constant I just calculated there over years. And our time is 5 years. So in case you weren't sure what I was talking about a second ago in terms of units, this is what I'm talking about. Your decay constant will have time units, which in this case is years, and your time should obviously have units, and it is years. And sometimes those units are not the same. So you do have to sometimes do a conversion to get them to the same. Otherwise, they will not cancel out correctly. In this case, we're all good. They're both in years, so everything's going to cancel out correctly. 1/years times years, there goes those units basically. So if we clean up everything on the right-hand side here, we'll take the natural log of 1.35, hit equals, we'll subtract, open up a parentheses, 0.2424 times 5. That's going to get me a natural log of A is equal to negative 0.911895. To get rid of the natural log, we're going to take the E of both sides. They're going to E that guy, going to E that guy right there. That's going to get rid of the natural log. And that will give us a final sort of concentration of 0. We'll call it 402. The units here are going to be the same units as the original concentration, which was 1.35 milligrams. First off, any questions on the calculation? This is good because it's going through radioactive decay, which means my concentration should start to decrease over time. And it went down from 1.35 to 0.402. If you did this and your concentration went up, you're definitely going in the wrong direction. Yeah, so it should be decreasing here with time. Any questions on that there? All right, we're going to lay it up there for